Welcome back to this logic synthesis tutorial. We're gonna pick up where we stopped last time with task number 8. So what are we doing in task number 8? We're gonna change our synthesis script just a little bit, and we're gonna add one additional step. This step is called incremental. It's part of the synthesis OPT command, but we add this option -incremental. So what we're doing is we go from a 3-step flow to a 4-step flow, basically. And we're asking the tool to work a little bit harder, to do a couple more iterations of its internal tricks to try to get us slightly better results, right? We're gonna keep everything else the same. We're gonna keep using high effort. We're gonna still prevent the usage of that AUI to 2 cell, same clock period, same everything. This is what we get when we use incremental OPT. We see a small increase in area, not really significant, and we see a small decrease in power, both static and total, okay? But it's a very, very small decrease. We can see on the terminal the values here, 0.009 and 2.58, okay? So this is what we did, this is what we achieved with this incremental OPT. Maybe other designs would benefit a little bit more. It's unclear. You would have to try it out. But the point is that now we have a script that is really good, right? We have basically turned on every single optimization we can think of. The question then becomes, can we push the clock period a little bit further, right? Our script is better. We're also allowing the usage of SLVT cells, right? This surely should help. So how do we do this? How do we reason about the clock period? Can we shrink the clock period? Can we increase the frequency? I could just blindly keep running synthesis runs and shrink the clock period. Or I could do something a little bit clever. I could look at my timing report, look at which cells are being used, and try to reason if there are opportunities for improvement. So let's scroll up. Let's find our timing report. It is right here. This is our critical path. Okay, starts at a flip-flop and then has a bunch of combinational logic. There's some sort of Wallace tree here in the middle. So this is some heavy arithmetic that is going on. It's a very long path. It has, I don't know, 20 plus cells in it. Okay, but the point is, we can look at which type of cells were used to figure out if there's a chance that we can improve our clock period, if we can improve our critical path. How do we do this? We just look at the suffix of these cells. If they have L, it means they are LVT cells, SL is SLVT, and then R is regular VT. So look at this cell right here. This is in our critical path. There is one regular VT cell in our critical path. Not only that, the size of the cell is P33. So it's 0.33 the nominal size. So it's not upsized at all. It's not buffed up at all. This is a very strong indication that our critical path can be improved if we adjust, push the clock period, okay? Let's take a look at the results we get from our new script for different clock periods, right? So here we're using the same 706 that we started with and then went down to 700 and 690 picoseconds. What's the trend here? For area, it's pretty obvious. As we shrink the clock period, area goes up. Dynamic power, which dominates, right? The total power also goes up. But then we have a couple numbers that are difficult to explain for static power. There are heuristics involved here, so we've got to take that into account. But there's also an explanation to why these numbers are the way they are, okay? So we see here that we start from 009, it goes up to 99, and then goes down to 86. This is counterintuitive. What happens is that we have two effects happening at the same time. So we're pulling these numbers from two different directions. Why does static power go up? Well, static power follows the number of cells that you have in your design. The more transistors you have, the more they leak. So this is an explanation why we go from 90 to 99. Why do we go from 99 to 86 or 90 to 86? As we shrink the clock period, we are keeping the cells active longer. We're doing more computation within that time. If you think of the clock period percentage-wise, how much of that clock period is a cell active doing something because there are inputs toggling versus how often the cell is idle, right? This is what happens when we shrink the clock periods. We kind of mess with that balance. We mess with those ratios. So now, proportionally, the cells spend more time burning dynamic than burning static. And that's why this number goes down. If we keep increasing the clock frequency, eventually this number tends to go to zero, which is insane. But it goes to zero because the cells are active all the time doing something. Okay, it is what happens. One other result I wanted to show to you is this one. We added another row to our table, and now we're doing synthesis at 686 picoseconds. And now we're not passing timing anymore. We have a slack violation of -6. But what we can check is actually where is our critical path for this version running at 686. This is what our critical path looks like. It is a fully combinational path. It's an in to out path. But what I wanted to show you is the suffix of all the cells that are employed here. SL, 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 SL. We cannot get faster than this. SL is the fastest version of the library that we have. So we need something else to fix the timing problem. And this path, if we want to keep increasing our clock period. This something else is pipelining, and that's what we're going to explore in task 9. Here we are, task 9, pipelining. Okay, what we have identified, our design has a bottleneck. It is an in to out path. Okay, it starts at address 2 and ends at read data 13. Okay, and it's a fully combinational path in to out. First thing I want to mention is that this should not happen, right? This is strange. It should not happen. Good RTL coding practice is to register all the outputs, make them reach a flip-flop. They shouldn't be combinational. But let's ignore that and let's work within the constraints that we have. How do we fix this problem? We fix this problem by adding a pipeline stage, exactly as shown on the figure. Our output used to be called read data. Now we're going to create a new output that is read data pipe, okay, by adding one flip-flop to the output. So now we cut this in to out path. It becomes into reg and reg to out, okay? Let's have a look at the code that we have for this. Here's the code. This code is provided to you in the file called SHA-256_pipe.v. What we did, okay, the previous outputs of this design, they used to be called read data and error. We are gonna synchronize them with the clock and put them on flip-flops, read data pipe and error pipe. And these become the new outputs. That's all the changes that we did to the RTL. Really, really simple changes, okay? Now, conceptually, what are we hoping that's gonna happen? Let's talk about the trade-offs involved in pipeline. The latency trade-off is obvious. We are adding one clock cycle latency to this design, right? It has to go through this flip-flop before the outputs become available. That's an obvious trade-off. We're also conceptually increasing the area of the design, because all these flip-flops that we're going to insert for all the outputs, right? I only have one bit represented here in the image, but we're going to do it for all of them. These flip-flops are not free, right? They take area. In terms of energy and power, again, these flip-flops are not free. They're going to burn power, right? So conceptually, what we think is going to happen is an increase in area and energy. Now, Let's look at our results and see if that is the case. Here are our results. Now, everything about these results is counterintuitive. Nothing makes sense. We see that we fixed the slack. That's great, right? Now slack is 0. It went from negative to 0, so we're passing timing. But look at area and cell count. It went down. Look at static power and total power. Both went down. How is this possible? We're adding logic to the design, and the design is becoming smaller and more power efficient. The reason is that we are making the time enclosure process much, much easier when we added the new stage of logic with the additional flip-flops. So a lot of the paths that were going through that part of the circuit were extremely buffered and using mostly the super fast cells, the SL cells. Once we add that flip-flop in there, those paths become much, much easier to close. So you can remove some of the buffers. You can downsize some of the cells. This is how you save area. If you save area, you save static power immediately, okay? You also have less logic toggling because you remove all the buffers. You will also get some savings in dynamic power once you do that. And for this particular case, these savings offset the increase that you have from new flip-flops. So this is all very interesting, a little bit counterintuitive, but this is what happens when you do this simple change to the design and add one stage of logic. And here we go with task 10, retiming. That's our last task for this two-part tutorial. Okay, we're gonna have a look at the critical path that we got from task 9, and we're gonna reason if it is even worth pursuing retiming. Okay, we need something to be there in order for us to have confidence that retiming is worth it. Let's go to the terminal. And here is my critical path, right? This is before retiming. We didn't apply retiming yet. We see that this is a reg to reg path. It starts at a flip-flop called core WMEM and ends at a flip-flop called core ereg. And we see that the slack is 0. Right? So this is our critical path. It has a slack of 0. What we can do is we can look at the neighboring stages of logic to the left and to the right. Let's start with the one to the left, the one that comes before this flip-flop right here. How do we do that? We do report timing -2 that flip-flop. So we're looking at a path that ends at that flip-flop. That's what the to argument does. And we see that this path has a huge slack, 368 picoseconds. That's interesting. So this is what we have on the left of our original critical path. Now let's go back here and let's copy the name of this flip-flop. This is the where our critical path ends. We're gonna see what is on the right of this path. So we're gonna do the from option in the report timing. So we're looking for a path that actually starts there. This is what we get. So this is a reg to reg path, and we see that there is a slack of 100 picoseconds. That's interesting. So let's visualize what that means. This is what we have. We have our critical path here with a slack of 0 seconds. To the left, we have another stage of logic that has a 368 picosecond slack, very significant slack, right? Our clock period is only 600 and something. And to the right, we also have another logic stage that has significant slack. All of that being said, retiming is going to work wonders here, right? This is what we hope retiming is going to achieve. It's going to take those flip-flops and move them with respect to the combinational logic to find paths that are more balanced. So we're going to take that extra 368 from here, extra 100 from here, and we're going to distribute over the 3 logic stages. And hopefully this path here that was really hard to close now will be easier to close. Okay, How do we do this? Well, retiming is a complicated engine, but basically it adds flip-flops that were not part of the original design to do this strategy of rebalancing. Let's have a look at the results. Here are the results for retiming. So initially, we see a significant increase in area, okay, and cell count. We see also a significant increase in total power, okay. This is because we're adding more logic. The design is bigger. We have more flip-flops than we used to have before. There's a command called report retime that you can use to check how many flip-flops were inserted. And for our design, this is more than 100 new flip-flops that were inserted. But what's the benefit of doing this? Okay, this design is now bigger, more power hungry. What exactly am I gaining out of this? What you're gaining is performance. If I move the clock frequency, the clock period, if I shrink the clock period to 500 picoseconds, I can still meet timing on this design. Remember what we said at the very beginning, 500 picoseconds used to be our impossible clock period. It's actually very possible and very doable with retiming. What's the drawback? You will pay a price in area and cell count and also in power, okay? Your numbers are gonna go up. That's it. That's the end of the video. We cover pipelining, we cover retiming. I have a few suggestions here at the end. There are some concepts that didn't appear at this video. If you want to do proper power estimation, consider using VCD files, so you actually use realistic inputs in your power estimations. We didn't talk about clock uncertainty. Everything we did, the clock was ideal. We didn't talk about DFT insertion, but there's a whole flow how to do insertion of test capabilities, right? DFT. And we also didn't talk about a different flow within Genus where you do a floor plan aware design. So you kind of take some hints from physical synthesis, that is the floor plan, and then you get a better result during logic synthesis. But those are kind of homework assignments, if you will. We're gonna wrap up this video here. Thanks for watching.